In January 2024, astronomers using the James Webb Space Telescope pointed their instruments at a seemingly ordinary patch of sky. What they found was not ordinary. They found a galaxy so large that it shouldn't exist according to our models. A galaxy so massive that it challenges our understanding of how structures form in the universe. A galaxy that, if our measurements are correct, is the single largest gravitationally bound structure ever discovered. We're calling it Alcyoneus, and it's about 16.3 million light-years across. To put that in perspective, the Milky Way, our home galaxy, is about 100,000 light-years across. Andromeda, the largest galaxy in our local group, is about 220,000 light-years across. The previous record holder for largest known galaxy was about 5 million light-years across. Alcyoneus is more than 3 times larger than that. This isn't just a record-breaking discovery. It's a galaxy that forces us to reconsider what we think we know about the universe. How did it get so big? Why does it exist at all? And what does its existence tell us about the limits of cosmic structure formation? In this video, we're going to explore what makes Alcyoneus extraordinary, why it's challenging our models, what it reveals about the history and future of the universe, and why some astronomers think there might be even larger galaxies out there that we just haven't found yet. This is the story of the biggest galaxy in the universe, and it's a story that's stranger than anyone predicted. Section 1. What we're actually looking at. Before we can understand why Alcyoneus is so important, we need to understand what it actually is. Because when I say galaxy, you probably picture something like the Milky Way, a spiral disk of stars rotating around a central bulge, maybe with some graceful spiral arms stretching outward. Alcyoneus is nothing like that. Alcyoneus is what's called a radio galaxy. Specifically, it's a giant radio galaxy, which is a category unto itself. And to understand what that means, we need to talk about the monster at its heart. At the center of Alcyoneus is a supermassive black hole. Not unusual. Most large galaxies have supermassive black holes at their centers. The Milky Way has one called Sagittarius, a star, with a mass of about 4 million times the Sun. But the black hole at the center of Alcyoneus is far more massive. Current estimates put it at around 400 million solar masses. That's 100 times more massive than our galaxy's central black hole. And this black hole is active. It's feeding. Gas and dust spiral into the black hole through an accretion disk, heating to millions of degrees as they fall inward. This process releases enormous amounts of energy, far more than the entire galaxy produces through stellar fusion. But not all the material falls into the black hole. Some of it gets caught up in the black hole's magnetic field and is ejected at nearly the speed of light in 2 narrow jets perpendicular to the accretion disk. These jets shoot out from the galactic core, carrying matter and energy into intergalactic space. And here's where Alcyoneus becomes extraordinary. Most active galactic nuclei have jets that extend for tens or hundreds of thousands of light years. Some of the most powerful extend for a few million light years. Alcyoneus's jets extend for over 16 million light years, from one end to the other. That's the diameter we're talking about when we say it's the largest galaxy. The jets themselves create vast lobes of radio-emitting plasma. These lobes are what make Alcyoneus visible as a radio source. In optical wavelengths, you'd see a relatively normal elliptical galaxy. But in radio wavelengths, you see this enormous structure stretching across the cosmos. The lobes are filled with energetic particles, electrons and protons accelerated to relativistic speeds. These particles interact with magnetic fields, producing synchrotron radiation that we detect as radio waves. The lobes glow in radio frequencies, like neon signs against the darkness of intergalactic space. So when we say Alcyoneus is 16.3 million light-years across, we're not talking about a disk of stars that large. We're talking about the total extent of its radio lobes, the region of space dominated by energy and matter ejected from this galaxy's supermassive black hole. But here's what makes this discovery particularly significant. These lobes are not ephemeral. They're not just transient structures that dissipate quickly. The plasma in these lobes is relatively long-lived. The particles retain their energy for tens or hundreds of millions of years, continuing to emit radio waves the entire time. This means Alcyoneus has been maintaining these jets, pumping energy into these lobes for an enormous span of time. We're looking at a galaxy that has been continuously active, continuously feeding its central black hole, continuously ejecting jets for potentially hundreds of millions of years. That level of sustained activity is itself remarkable, and the size it's achieved is unprecedented. Section 2: How we found it. The discovery of Alcyoneus is itself a story worth telling because it reveals something important about how modern astronomy works and how many discoveries are still waiting to be made in data we've already collected. Alcyoneus was not found by pointing a telescope at a specific target. It was found through data mining, systematically analyzing massive datasets of radio observations, looking for interesting patterns. The discovery was made by a team led by Martijn Ooi at Leiden Observatory in the Netherlands. They were working with data from the Low Frequency Array, or LOFAR, a radio telescope network spread across Europe, with its core in the Netherlands. LOFAR is different from traditional radio telescopes. Instead of a single large dish, it's composed of thousands of small antennas spread across multiple countries. These antennas work together through a technique called interferometry, effectively creating a telescope the size of a continent. The advantage of this approach is sensitivity and resolution. LOFAR can detect extremely faint radio sources and can map the sky in extraordinary detail. The disadvantage is data volume. LOFAR generates petabytes of data, far too much for humans to analyze directly. So researchers developed algorithms to automatically scan the data, looking for specific patterns. In this case, they were looking for radio lobes, the signature of active galactic nuclei with jets. The algorithm flagged Alcyoneus as an anomaly. The radio lobes were so large that they didn't fit the typical profile. At first, the team thought it might be an error, perhaps two separate sources that the algorithm had incorrectly associated. But when they examined the data more carefully, they realized it was real. The morphology was right. The lobes were clearly connected to a central source. The spectral characteristics matched what you'd expect from synchrotron radiation in giant radio lobes. And when they calculated the angular size on the sky and estimated the distance to the source, they realized they were looking at something enormous, far larger than any previously known radio galaxy. The distance estimate is crucial here. Alcyoneus is about 3 billion light-years away from us. That means we're seeing it as it was 3 billion years ago. The light and radio waves we're detecting were emitted when the universe was about 11 billion years old. At that distance, even an object millions of light-years across subtends only a small angle on the sky. You need very high-resolution observations to resolve the structure. LOFAR had exactly the resolution needed. But here's what's particularly interesting. LOFAR has been observing this part of the sky for years. The data that revealed Alcyoneus was already in the archives. No one had noticed it before because no one had looked at the data in quite the right way or with quite the right algorithms. This suggests something important. There might be more discoveries like this waiting in existing data. More giant radio galaxies that are so large, so extended, so faint in surface brightness that they've been overlooked by previous surveys. The discovery of Alcyoneus isn't just, we found the biggest galaxy. It's, we found the biggest galaxy so far, and our methods for finding such objects are just getting started. There could be bigger ones out there, and if there are, we're now in a position to find them. Section 3, Why it shouldn't exist. Here's where things get uncomfortable for cosmologists. Alcyoneus shouldn't exist. Not in the sense that it's physically impossible, but in the sense that our models of structure formation in the universe don't predict galaxies this large should form. Let me explain the problem. Galaxies form through a hierarchical process. Small structures form first, then merge to form larger structures, which merge to form larger structures still. This process is driven by gravity and plays out over billions of years. We can simulate this process on computers. We input the initial conditions from the early universe, the slight density fluctuations left over from the Big Bang, and we let the physics run forward. Gravity pulls matter together. Dark matter halos form. Normal matter falls into these halos. Galaxies assemble. These simulations are extremely sophisticated. They account for dark matter, normal matter, gas dynamics, star formation, supernova feedback, black hole accretion, AGN jets, all the known physics that affects galaxy formation. And these simulations are pretty good. They reproduce the observed distribution of galaxies, the typical sizes and masses, the relationships between galaxy properties. They match observations reasonably well, but they don't produce galaxies like Alcyoneus, at least not commonly. The issue is the jets. To create radio lobes 16 million light-years across, you need jets that have been active for an extremely long time. The jets propagate through intergalactic space at a significant fraction of the speed of light, but they still need hundreds of millions of years to reach such distances. During that time, the central black hole must remain active. It must continue accreting matter at a high rate. It must continue launching jets. This requires a steady supply of gas falling toward the black hole. But in simulations, black hole activity tends to be episodic. The black hole turns on, accretes material, launches jets. This heats the surrounding gas, which stops the inflow of fresh material. The black hole's activity declines. It turns off. Eventually, gas cools and begins falling in again. The black hole reactivates. But there's been a gap, a period of inactivity. This on-off cycle is what we expect, and it's generally what we observe. Most radio galaxies show signs of multiple episodes of activity. old, faded lobes from past episodes, new, bright lobes from current activity. But Alcyoneus appears to show continuous activity over a timescale of hundreds of millions of years. No obvious gaps, no clear evidence of episodic behavior, just sustained, continuous jet activity. This is hard to explain. What allows Alcyoneus to maintain such steady activity? Does it have an unusually large reservoir of gas? Is it in a particularly dense environment that continuously funnels material toward the black hole? Is there something about its black hole or its accretion process that's different from typical galaxies? We don't know, and that's the problem. There's another issue: the energy requirements. Maintaining jets that create lobes this large requires enormous energy output. The black hole must be converting mass to energy at a prodigious rate. The total energy content of the lobes is estimated to be on the order of 10 to the power of 60 ergs. That's a billion times 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 the energy content of a typical supernova. Where does all that energy come from? How much mass has fallen into the black hole to power this? And how has the galaxy managed to supply that much material without running out? The numbers work out to roughly 100 million solar masses of material converted to jet energy over the lifetime of the lobes. That's a lot. It's not impossible. The black hole has 400 million solar masses total, so in principle it could have accreted this much. But it requires very efficient feeding over a very long time. Most galaxies don't achieve this. Most don't have access to that much material in a form that can be accreted. Most experience phases where the black hole is starved, where jets shut off, where growth stops. Alcyoneus is an outlier, a statistical anomaly, something that shouldn't be common according to our models. And that raises a question. If our models don't predict galaxies like this, what else are our models missing? What other surprises are waiting in the data? Section 4. The environment around Alcyoneus. To understand why Alcyoneus is so large, we need to understand where it is and what surrounds it. Because galaxies don't exist in isolation. They're embedded in a cosmic web of matter, filaments of galaxies connected by gas and dark matter, surrounding vast, empty voids. The environment a galaxy finds itself in has profound effects on its evolution. Galaxies in dense clusters behave differently from galaxies in isolation. They interact with neighbors, experience Raum pressure from hot intracluster gas, and can be tidally stripped or even cannibalized by larger galaxies. So where is Alcyoneus? What's its neighborhood like? This is where the story gets interesting, because Alcyoneus is not in an unusually dense environment. It's not at the center of a massive galaxy cluster where you might expect to find the most extreme objects. It's not in a rich group surrounded by dozens of large neighbors. It's relatively isolated. It sits in a region of moderate density. Not a void, but not a cluster either. A fairly typical cosmic environment. This is surprising. One of the leading theories for why some radio galaxies develop such large lobes is environmental. The idea is that jets propagating through low-density environments can extend further before they're slowed down by interactions with intergalactic gas. In dense environments, there's more gas. The jets plow through this gas, creating strong shocks, losing energy, eventually stalling. In low-density environments, there's less resistance. The jets can propagate further on the same energy budget. So you'd expect the largest radio galaxies to be in underdense regions, voids or the outskirts of clusters where there's very little intergalactic gas to slow the jets down. Alcyoneus is not in such a region. It's in a typical environment, which means it achieved its enormous size not because it faced unusually little resistance, but through some intrinsic property of the galaxy itself. This points back to the central black hole and the duration of its activity. Alcyoneus is big not because its jets had an easy path, but because its jets ran for an exceptionally long time with exceptional power. But the environment does tell us something else important. The intergalactic gas around Alcyoneus has been affected by the radio lobes. The lobes deposit enormous amounts of energy into the surrounding medium. This energy heats the gas, creates shocks, drives turbulence. Observations suggest that the gas around Alcyoneus has been significantly disturbed. The radio lobes have carved out cavities in the gas distribution. The temperature and density structure of the intergalactic medium around the galaxy shows clear signs of energy injection. This is called AGN feedback. Active galactic nuclei don't just pump energy into their jets, they affect the entire region around their host galaxy. This feedback can suppress star formation by heating gas and preventing it from cooling and collapsing. It can drive gas out of galaxies entirely. It plays a crucial role in galaxy evolution. Alcyoneus is an extreme example of AGN feedback. Its influence extends not just across its host galaxy, but across a region tens of millions of light years across. It has thermally and dynamically affected an enormous volume of space. What does this mean for neighboring galaxies? There aren't many close neighbors, but the ones that exist are bathed in this energetic environment. Their own gas reservoirs might be affected, their star formation might be suppressed. They're living in the aftermath of Alcyoneus's sustained, violent activity. In a sense, Alcyoneus is a cosmic bully. It's not just passively existing in its environment. It's actively reshaping that environment on scales far larger than the galaxy itself. Section 5. The jets, how they work and why they're so powerful. Let's dive deeper into the mechanism that creates these enormous lobes. Because understanding the jets is key to understanding why Alcyoneus achieved such size. The jets launched by active galactic nuclei are among the most powerful phenomena in the universe. They're driven by the immense gravitational energy of material falling into a supermassive black hole. Here's how they work at a basic level. Material in the accretion disk around a black hole is orbiting at a significant fraction of the speed of light. It's extremely hot, millions to billions of degrees, and it's threaded with magnetic fields. These magnetic fields, anchored in the accretion disk and twisted by the disk's rotation, are believed to be responsible for launching the jets. The exact mechanism is still debated, but the leading theory involves what's called the Blandford-Znajek process. In this process, the magnetic fields threading through the black hole's ergosphere, the region just outside the event horizon, where space itself is dragged around by the black hole's rotation, extract energy from the black hole's rotation and funnel it into narrow jets perpendicular to the disk. These jets are composed of plasma, a mix of electrons, protons, and magnetic fields, accelerated to velocities very close to the speed of light. The energy density in the jets is enormous. A single jet from a powerful AGN can carry as much power as the combined light from trillions of stars. As the jets propagate away from the black hole, they maintain their collimation through magnetic fields. The fields act like a nozzle, keeping the jet focused into a narrow stream rather than allowing it to disperse. But eventually, thousands or millions of light years from the black hole, the jets begin to decelerate. They run into intergalactic gas, diffuse but present. This gas creates resistance. The leading edge of the jet slows, while material behind continues to flow forward. This creates a structure called a hot spot. The hot spot is where the jet terminates, where the fast-moving plasma from the jet collides with the slower-moving plasma that's already accumulated. It's a region of intense shocks and particle acceleration. Behind the hot spot, the plasma inflates into a lobe. This lobe is continuously fed by the jet, growing larger over time. The lobe itself is buoyant. It's less dense than the surrounding intergalactic medium. So it rises, moving away from the galactic plane, creating the classic double-lobed structure we see in radio galaxies. Now, here's what's special about Alcyoneus. Its jets have been powerful enough and sustained enough to create lobes extending over 16 million light years. That requires several things going right simultaneously. First, the jets need to be powerful. Weak jets would be disrupted or slowed by interactions with intergalactic gas long before reaching such distances. Alcyoneus's jets are carrying enormous power, estimated at around 10 to the power of 45 ergs per second. That's 100 billion times the total power output of the Milky Way. Second, the jets need to be stable. Jets can become unstable through various mechanisms: kink instabilities in the magnetic field, turbulence, interactions with ambient gas. Unstable jets break up, losing their collimation and their ability to propagate effectively. Alcyoneus's jets have remained stable across millions of light years. Third, the jets need to run continuously. If there are gaps in the jet activity, periods where the black hole turns off, the lobes would fade during those gaps. Material in the lobes gradually loses energy through radiation and adiabatic expansion. Without continuous replenishment from the jets, the lobes become undetectable in radio wavelengths. The lobes of Alcyoneus are clearly visible, which means the jets have been active essentially continuously for the entire time it took to build these lobes. That's several 100 million years of sustained activity. This combination, powerful jets, stable jets, continuous jets, is what sets Alcyoneus apart. Most radio galaxies fail on at least one of these criteria. Their jets are weaker or less stable, or more episodic. Alcyoneus has somehow maintained optimal conditions for jet growth for an extraordinarily long time. Section 6. What this tells us about black hole growth. The existence of Alcyoneus gives us a window into one of the most important processes in galaxy evolution: how supermassive black holes grow and how their growth affects their host galaxies. Black holes at the centers of galaxies don't start out supermassive. They grow over time by accreting matter and by merging with other black holes when galaxies collide. The growth rate is limited by something called the Eddington limit. This is the maximum rate at which a black hole can accrete matter before the radiation pressure from the infalling material becomes strong enough to push away additional material. For a black hole of a given mass, the Eddington limit sets a maximum luminosity and a maximum accretion rate. In practice, this means a black hole can grow at most at a rate proportional to its current mass. It takes time, tens to hundreds of millions of years, to grow from a stellar mass black hole to a supermassive one. But here's the complication. Most of the time, black holes aren't accreting at anywhere near the Eddington limit. They're starved. There's not enough gas in the right configuration to feed them efficiently. They grow in fits and starts, with long periods of low activity, punctuated by occasional bursts when gas becomes available. Alcyoneus's black hole appears to be different. To sustain the jets we observe requires accretion at a significant fraction of the Eddington limit, sustained over hundreds of millions of years. This is unusual. What does this tell us? Several things. First, it tells us that Alcyoneus has had access to an enormous reservoir of gas. Either it's been continuously supplied with fresh gas from its surroundings, or it had a massive gas reservoir to begin with that it's been consuming over time. Observations suggest it's a combination of both. Alcyoneus appears to have a rich gas content in its central regions, the result of past interactions with other galaxies that funneled gas toward the core. And it continues to accrete gas from its environment at a steady rate. Second, it tells us that the accretion process has been remarkably stable. Black hole accretion is complex. The gas forms an accretion disk, which can be unstable to various perturbations. The jets themselves can disrupt the inflow of gas, creating a negative feedback loop that shuts down accretion. Most systems experience this feedback. The black hole turns on, launches jets, heats the surrounding gas, and thereby shuts off its own fuel supply. After a period of dormancy, gas cools and begins accreting again, and the cycle repeats. Alcyoneus has somehow avoided this cycle, or at least has experienced much longer on phases than typical. This suggests something special about its accretion geometry, or its gas supply, that allows sustained feeding. Third, it tells us about the co-evolution of black holes and galaxies. There's a well-established correlation between the mass of a galaxy's central black hole and the properties of the galaxy itself, specifically the mass of the central bulge and the velocity dispersion of stars in that bulge. This correlation suggests that black holes and galaxies evolve together, influencing each other through feedback processes. The growth of the black hole affects the galaxy by heating gas and regulating star formation. The growth of the galaxy affects the black hole by funneling gas toward the center. Alcyoneus is an extreme case of this co-evolution. Its black hole has grown to 400 million solar masses. Its jets have deposited enormous energy into the surrounding medium, affecting not just the host galaxy, but the intergalactic environment out to distances of millions of light years. This is feedback on a scale rarely observed, and it raises questions about how common such extreme feedback is in the universe, and what long-term effects it has on cosmic structure. Section 7. Comparison to other giant radio galaxies. Alcyoneus is the current record holder, but it's not alone. There are other giant radio galaxies, GRGs, in the literature, and comparing Alcyoneus to them helps us understand what makes it special and what patterns might exist among these extreme objects. Before Alcyoneus, the largest known radio galaxy was another GRG discovered a few years earlier. with lobes extending about 5 million light years. There are about 100 confirmed giant radio galaxies in the literature, defined as having a total extent larger than about 2 million light years. All of these galaxies share certain characteristics. They all have supermassive black holes at their centers, typically in the range of 100 million to 1 billion solar masses. They all show powerful jets and extended radio lobes. They're all relatively old systems, having maintained jet activity for hundreds of millions of years. But within this population, there's diversity. Some GRGs are in rich cluster environments. Others, like Alcyoneus, are relatively isolated. Some show clear evidence of past mergers with other galaxies. Others appear to have grown more quietly. The orientation of the jets relative to our line of sight also varies. Some GRGs are oriented edge-on, so we see the full extent of both lobes. Others are oriented more face-on, which can make them harder to detect and measure accurately. Alcyoneus is particularly well-oriented for measurement. We're seeing it at a favorable angle that allows us to trace both lobes from end to end. This is one reason we can be confident about its size. We're not dealing with projection effects that might artificially inflate or deflate the measured extent. Statistically, giant radio galaxies are rare. They make up less than 1% of all radio galaxies. Most radio galaxies are much smaller, with lobes extending only hundreds of thousands of light years. This rarity suggests that the conditions needed to produce GRGs are special. Not every galaxy with a supermassive black hole can create such extended structures. There must be specific factors: the environment, the gas supply, the stability of the jets, the duration of activity, that distinguish GRGs from typical radio galaxies. Alcyoneus represents the extreme end of this distribution. If GRGs are rare, Alcyoneus is exceptionally rare. It's the 1 in a billion object that pushes every parameter to its limit. But here's what's interesting. If you plot the distribution of radio galaxy sizes, there's no obvious cutoff at the size of Alcyoneus. The distribution appears to continue smoothly, suggesting that even larger galaxies might exist. They'd be harder to find, of course. Larger size means lower surface brightness. The radio emission is spread over a larger area, making it fainter per unit area. Current radio surveys have sensitivity limits. An object larger than Alcyoneus, but with slightly lower surface brightness, might fall below detection thresholds. This is why the discovery of Alcyoneus is significant, not just for being the largest currently known, but for demonstrating that our surveys are now sensitive enough to detect objects at this scale. Future surveys, with better sensitivity and coverage, might reveal even larger galaxies. The distribution suggests they're out there. We just need to look carefully enough to find them. Section 8. The magnetic fields. One aspect of Alcyoneus that deserves special attention is the magnetic fields permeating its jets and lobes. Because these fields are not just a detail, they're fundamental to how the jets work and how the lobes persist. Magnetic fields in astrophysics are often underappreciated. They're invisible in most types of observations. We usually infer their presence indirectly, through their effects on charged particles or through polarization of emitted light. In radio galaxies, magnetic fields are central to the physics. The jets are essentially streams of magnetized plasma. The magnetic fields help collimate the jets, keeping them narrow and focused across enormous distances. Without magnetic confinement, the jets would disperse, losing their power and effectiveness. In the lobes, magnetic fields play a different role. The energetic electrons in the lobes spiral around magnetic field lines, emitting synchrotron radiation, the radio waves we detect. The intensity and spectrum of this radiation tell us about the strength and structure of the magnetic fields. For Alcyoneus, observations provide estimates of the magnetic field strength in the lobes. It's weak by laboratory standards, about a microgauss or 1/1,000,000th of the Earth's surface magnetic field. But weak fields can have strong effects when they pervade such enormous volumes. The total magnetic energy in Alcyoneus's lobes is substantial. It contributes significantly to the total energy budget of the system. And the fields provide structural support. They help the lobes maintain their shape against pressure from the surrounding intergalactic medium. There's an interesting question about the origin of these fields. Magnetic fields in the lobes are ultimately derived from the fields in the accretion disk around the black hole. But those fields have been amplified, stretched, and twisted by the dynamics of the jets and lobes. Turbulence in the jets can amplify magnetic fields. Shear flows can stretch field lines. Shocks at the hot spots can compress and strengthen fields locally. The result is a complex magnetic field structure that varies across the lobes. Polarization observations, which measure the orientation of the magnetic field based on the polarization of the synchrotron radiation, show that Alcyoneus's lobes have organized, large-scale magnetic field structures. The fields are not completely tangled and random. There's coherence, suggesting that the fields have been ordered by the large-scale flow patterns in the lobes. This is important for understanding the long-term evolution of the lobes. Ordered magnetic fields are more stable than random fields. They help the lobes resist disruption and maintain coherence over hundreds of millions of years. Without strong, organized magnetic fields, the lobes might fragment, mix with the ambient medium, and dissipate much faster. The fields are one reason Alcyoneus has been able to grow to such size. They provide the structural integrity needed for the lobes to persist as distinct entities across such vast distances. Section 9. The radio spectrum and what it reveals. Another way to understand Alcyoneus is through its radio spectrum. How the intensity of radio emission varies with frequency. Radio galaxies emit radio waves across a wide range of frequencies, from about 10 megahertz to over 10 gigahertz. Different parts of this spectrum tell us different things about the physical conditions in the jets and lobes. The spectrum of synchrotron radiation depends on the energy distribution of the electrons and the strength of the magnetic field. High-energy electrons radiating in strong magnetic fields produce high-frequency radio waves. Low-energy electrons in weak fields produce low-frequency waves. By measuring the radio spectrum at many frequencies, we can infer the energy distribution of electrons in the lobes and how that distribution evolves over time. For Alcyoneus, the radio spectrum shows something interesting. It's steep. This means the intensity drops off rapidly with increasing frequency. In technical terms, the spectral index is steep. A steep spectrum indicates that the high-energy electrons, the ones that produce high-frequency radiation, are depleted relative to low-energy electrons. This is a signature of aging. High-energy electrons lose energy more quickly through synchrotron radiation and other processes. Over time, the population of electrons shifts toward lower energies, and the spectrum steepens. The fact that Alcyoneus's lobes show steep spectra tells us that the electron population is old. The electrons were accelerated long ago, hundreds of millions of years ago, and have been gradually losing energy since then. But the spectrum isn't uniformly steep across the lobes. The hotspots, where the jets terminate, show flatter spectra. This indicates fresh injection of high-energy electrons. The jets are still active, still delivering newly accelerated particles to the hotspots. This combination, steep spectrum in the lobes, flat spectrum at the hotspots, is consistent with continuous jet activity over a very long time. The lobes contain the accumulated remnants of particles accelerated throughout the history of the jets, while the hotspots show the signature of ongoing particle acceleration. There's one more spectral feature worth noting. At very low frequencies, below about 100 MHz, Alcyoneus shows enhanced emission compared to what a simple steep spectrum would predict. This is called spectral flattening or upturn. The cause is not entirely understood, but one possibility is free absorption, radio waves being absorbed by ionized gas in the environment surrounding the lobes. This absorption is stronger at low frequencies, so it suppresses the very lowest frequency emission and causes an apparent flattening of the spectrum. If this interpretation is correct, it tells us something about the gas content of the intergalactic medium around Alcyoneus. There's ionized gas out there in the space between galaxies, interacting with the radio lobes. This gas is important because it's part of the cosmic baryon budget, the accounting of where all the normal matter in the universe resides. Much of the universe's baryonic matter is not in stars or galaxies, but in diffuse gas in intergalactic space. Alcyoneus's radio emission allows us to probe this gas, to measure its density and ionization state in a way that few other observations can. Section 10. The energetics, power on cosmic scales. Let's talk about the sheer power output of Alcyoneus, because the numbers are staggering, and they tell us something fundamental about the most energetic processes in the universe. The radioluminosity of Alcyoneus, the total power it emits in radio wavelengths, is approximately 10 to the power of 42 ergs per second. To put that in perspective, the Sun's total luminosity across all wavelengths is about 4 times 10 to the power of 33 ergs per second. Alcyoneus's radio emission alone is more than 100 billion times the Sun's total output. And that's just the radio emission? The jets also carry kinetic energy, magnetic energy, and produce radiation across the electromagnetic spectrum. When you account for all forms of energy in the jets, the total power output is estimated at around 10 to the power of 45 ergs per second. That's 100 billion times the Sun's luminosity. It's roughly equal to the combined light output of 100 trillion sun-like stars. Where does this energy come from? Ultimately, from gravity. Matter falling into the black hole releases gravitational potential energy. As material spirals inward through the accretion disk, friction and magnetic stresses heat it to millions of degrees. This heated material radiates photons, and the radiation pressure and magnetic fields channel some of the energy into the jets. The efficiency of this process is remarkable. According to general relativity, Up to about 42% of the rest mass energy of infalling matter can be extracted if the black hole is spinning rapidly. That's far more efficient than nuclear fusion, which converts less than 1% of mass to energy. For Alcyoneus to sustain its current power output over the estimated age of the lobes, 300 million years, the black hole must have accreted roughly 100 million solar masses of material and converted a fraction of that mass to energy. That's an enormous amount of matter. It's equivalent to about 100,000 Earth mass planets every year, or about one sun mass star every 3 years, sustained for 300 million years. Where did all this material come from? Several sources: gas reservoirs in the galaxy. Elliptical galaxies like Alcyoneus's host can contain substantial amounts of hot gas in their halos. This gas can cool, lose angular momentum, and spiral into the black hole. Stellar mass loss. Evolved stars shed significant mass through stellar winds. In the dense central regions of galaxies, this stellar mass loss provides a steady supply of gas that can be accreted. Galaxy interactions. If Alcyoneus underwent mergers or tidal interactions with other galaxies in the past, these events would have funneled gas toward the center, providing fuel for the black hole. Cold gas flows. Simulations suggest that cold gas can flow along cosmic web filaments directly into galaxies, providing fresh fuel even without mergers. Probably all of these sources contributed, but the key point is that Alcyoneus has had access to an extraordinary fuel supply, sustained over hundreds of millions of years, to power its enormous jets. Section 11. Multi-wavelength observations. While Alcyoneus is most spectacular in radio wavelengths, it has also been observed across the electromagnetic spectrum. Each wavelength reveals different aspects of the physics at play. Optical observations show the host galaxy itself, a massive elliptical galaxy with a typical population of old red stars. There's no sign of recent star formation, which is expected for a galaxy of this type and age. The optical morphology is smooth and regular, with no obvious tidal features or signs of recent mergers. This is somewhat surprising given the intense activity at the center. It suggests that if Alcyoneus underwent mergers in the past, they happened long enough ago that the stellar distribution has relaxed to equilibrium. Infrared observations from telescopes like Spitzer and WISE detect thermal emission from dust in the galaxy. The dust is heated by starlight and by radiation from the active galactic nucleus. The infrared spectrum helps determine the rate of star formation and the amount of dust obscuration. For Alcyoneus, the infrared data shows moderate dust content, but low star formation. Most of the galaxy's stellar mass formed billions of years ago. The current star formation rate is low, perhaps a few solar masses per year compared to hundreds or thousands in actively star-forming galaxies. X-ray observations from Chandra and XMM Newton reveal hot gas in and around the galaxy. The X-rays come from two main sources: hot gas in the galaxy's halo, heated by stellar mass loss and supernova explosions, and very hot gas in the immediate vicinity of the black hole. The X-ray data also show inverse Compton emission, high-energy photons created when the energetic electrons in the radio lobes scatter low-energy photons up to X-ray energies. This emission traces the same electron population responsible for the radio emission, but reveals it through a different physical process. The X-ray observations are particularly valuable for studying the interaction between the radio lobes and the surrounding gas. Where the lobes contact the intergalactic medium, shocks form, heating the gas and creating bright X-ray emission. These shock fronts allow us to measure the pressure and density of both the lobes and the ambient medium. Gamma-ray observations from Fermi-Lat have been attempted but show no clear detection. This is not surprising. Most radio galaxies are not strong gamma-ray emitters unless the jets are pointed almost directly at us. For Alcyoneus, the jets are oriented more perpendicular to our line of sight, so we don't expect strong gamma-ray emission. However, very high-energy gamma rays could potentially be produced in the lobes through interactions between cosmic rays accelerated in the lobes and the ambient gas and radiation fields. Future, more sensitive gamma-ray observations might detect this emission. Ultraviolet observations are difficult for Alcyoneus because it's faint at these wavelengths and because there's substantial galactic foreground absorption. But UV observations can reveal hot, young stars or gas ionized by the AGN. For Alcyoneus, limited UV data suggests minimal contribution from young stars, consistent with the optical and infrared observations showing an old stellar population. The multi-wavelength picture that emerges is of a massive, evolved galaxy with an old stellar population, moderate gas content, and an extremely active nucleus that has been launching powerful jets for hundreds of millions of years. The jets dominate the energetics, outshining the entire stellar population in their total power output. Section 12, Theoretical Models and Simulations, Understanding How. Alcyoneus formed and evolved requires sophisticated computer simulations. These simulations attempt to recreate the physical processes: black hole accretion, jet launching, jet propagation, interaction with the environment, that produce giant radio galaxies. The simulations begin with initial conditions: a massive galaxy with a supermassive black hole at its center, embedded in a realistic cosmological environment with dark matter, gas, and neighboring galaxies. The code then evolves the system forward in time, solving equations that describe gravity, using n-body techniques to follow the motion of dark matter and stars, and solving Poisson's equation for the gravitational field. Hydrodynamics, treating gas as a fluid and solving equations for mass, momentum, and energy conservation. Magnetic fields, using magnetohydrodynamic (MHD) equations to follow the evolution of magnetic fields threading through the gas. Black hole accretion, modeling the flow of gas onto the black hole, using subgrid models since the scales near the black hole, astronomical units, are far smaller than the simulation can resolve, thousands of light years. Jet launching, implementing prescriptions for how accreting black holes launch jets, based on theoretical models like Blandford's and Hayek. Jet propagation, following the jets as they plow through the ambient medium, creating bow shocks, depositing energy, and inflating lobes. Radiative processes, calculating the emission and absorption of radiation, including cooling of hot gas, and feedback effects from radiation pressure. These simulations are computationally expensive. A single simulation of a giant radio galaxy might require millions of CPU hours on supercomputers. And many simulations are needed to explore parameter space, varying the black hole mass, the accretion rate, the jet power, the environmental density. The results are mixed. Simulations can produce radio galaxies with lobes extending millions of light years, roughly Matching observations. They reproduce the double-lobed morphology, the hot spots, the radio spectrum. But producing something as large as Alcyoneus requires fine-tuning. The jets need to be powerful, sustained, and stable. The environment needs to have the right density profile. The black hole needs to maintain high accretion for long periods. In simulations, achieving all these conditions simultaneously is rare. Most simulated radio galaxies are smaller than Alcyoneus. This matches the observational fact that giant radio galaxies are rare. What the simulations reveal is that Alcyoneus sits at the tail end of a distribution. It's not a completely different type of object requiring exotic physics. It's just an extreme example of normal radio galaxy physics pushed to the limit. The simulations also help us understand what we can't yet observe. For instance, they show that the jets are not smooth, continuous flows, but are turbulent, with instabilities, shocks, and time variability on scales too small for current observations to resolve. They show that the lobes are not homogeneous, but have a complex internal structure with filaments, knots, and variations in pressure and magnetic field strength. And they predict future evolution. According to the simulations, if Alcyoneus's jets continue at their current power for another 100 million years, the lobes could extend to 20 to 25 million light years. But if the jets shut off, the lobes would fade substantially within 50 to 100 million years, becoming undetectable to current radio telescopes. These predictions are testable in principle, though not in our lifetimes. Future radio surveys might catch Alcyoneus at a later stage of evolution, allowing comparison with model predictions. Section 13. The cosmic significance. Let's zoom out and ask the big question. What does Alcyoneus tell us about the universe as a whole? First, it demonstrates that the universe can produce structures far larger than individual galaxies through active processes. While gravitational collapse creates structures up to a few 100 million light years, galaxy superclusters, active galactic nuclei can create structures on tens of millions of light years scales through energy injection. This has implications for the energy budget of the intergalactic medium. The energy deposited by radio galaxies like Alcyoneus heats the gas between galaxies, affecting its temperature and preventing it from cooling and forming new galaxies. On cosmic scales, AGN feedback, including from radio galaxies, is thought to be one of the main processes regulating galaxy formation. Without it, simulations produce too many massive galaxies compared to observations. The energy from AGN prevents gas from cooling efficiently, suppressing star formation in the most massive systems. Alcyoneus is an extreme example of this feedback. Across a region tens of millions of light years wide, it has deposited enough energy to affect the thermal state of the gas and potentially suppress galaxy formation. Second, Alcyoneus shows that supermassive black holes can sustain high activity levels for hundreds of millions of years. This is longer than some theoretical models predicted. It suggests that fuel supply mechanisms are more efficient or long-lived than we thought. This has implications for black hole growth. If black holes can accrete at high rates for such long periods, they can grow faster than models based on shorter duration accretion episodes would predict. This might help explain how supermassive black holes grew to billions of solar masses in the early universe. Third, Alcyoneus provides a laboratory for studying relativistic jets in an extreme regime. The jets have propagated for millions of light years, encountering a range of environmental conditions, yet maintained their collimation and power. Understanding how they do this refines our models of jet physics, which apply not just to radio galaxies, but to other jet launching systems, like gamma-ray, bursts, and microquasars. Fourth, the existence of Alcyoneus tells us something about statistics. If objects this rare and extreme exist, it means the tail of the distribution of galaxy properties extends farther than we might have guessed. This has implications for predicting what else might be out there. For every Alcyoneus, there might be dozens of slightly smaller giant radio galaxies. For every giant radio galaxy, thousands of normal radio galaxies. The distribution matters for understanding the overall population and for planning future surveys. Finally, Alcyoneus reminds us that the universe still holds surprises. We thought we understood the basics of radio galaxies. We had models and theories that seemed to work. Then Alcyoneus appears and forces us to revisit our assumptions. This is how science progresses, not through sudden revolutions, usually, but through the gradual accumulation of observations that push at the edges of our understanding, revealing new phenomena and forcing theoretical refinement. Alcyoneus is one data point, but it's an important one, and it's a reminder that nature is more extreme, more diverse, and more surprising than our theories often assume. Section 14, the observational techniques in detail. Let me take you deeper into how we actually observe and measure an object like Alcyoneus, because the technical sophistication required is itself a remarkable achievement. Radio interferometry, the technique used to discover Alcyoneus, works by combining signals from multiple antennas spread across large distances. Each pair of antennas forms a baseline, and the interference pattern created when their signals are combined contains information about the structure of the radio source. For LOFAR, with thousands of antennas spread across Europe, there are millions of possible baselines. Each baseline is sensitive to structure on a particular angular scale. Short baselines detect large-scale structure. Long baselines detect fine details. To create an image of Alcyoneus, the data from all these baselines must be combined. This is done through a mathematical process called Fourier transformation. The raw data exists in visibility space, essentially a measurement of how correlated the signals are between different antenna pairs at different times. The Fourier transform converts this visibility data into an image showing the brightness distribution on the sky. But it's not straightforward. The data is incomplete. You don't have measurements for every possible baseline, and it's noisy. Creating a high-quality image requires sophisticated deconvolution algorithms that fill in the missing information while suppressing artifacts. For extended sources like Alcyoneus, there's an additional challenge. The lobes are faint and cover a large area on the sky. Traditional imaging algorithms are optimized for compact bright sources. They can miss extended emission or break it up into multiple spurious components. The team that discovered Alcyoneus used specialized techniques called multi-scale, clean, and direction-dependent calibration. These algorithms are designed to handle extended sources by modeling the emission on multiple spatial scales simultaneously and correcting for ionospheric distortions that vary across the field of view. The processing required is intensive. Creating a single high-quality image of a low-far field can require days of computation on supercomputers. The image used to discover Alcyoneus was part of a larger survey that took years to complete, processing petabytes of raw data into images covering hundreds of square degrees of sky. Once the image exists, finding sources like Alcyoneus requires automated source detection. Algorithms scan the image looking for pixels brighter than the background noise. They group connected bright pixels into sources and measure properties like flux, density, size, and morphology. But automated detection can miss extended, low, surface brightness structures. The signal is there, but it's spread over so many pixels that each individual pixel is only slightly above the noise level. The source becomes invisible to simple threshold-based detection. This is where machine learning is starting to play a role. Neural networks can be trained on simulated radio galaxies to recognize the characteristic morphology of giant radio galaxies, even when they're faint and extended. These networks can flag candidates that human observers or traditional algorithms would miss. Alcyoneus was found through a combination of traditional techniques and careful human inspection of the data. The automated pipeline flagged it as unusual, and researchers followed up with detailed analysis to confirm it was real and measure its properties. Measuring the size required determining the distance, which meant obtaining a redshift. For optical spectroscopy, you need to identify the host galaxy in optical images using surveys like SDSS or pan-STARRS. Get telescope time on a large optical telescope, observe the galaxy for long enough to get a good spectrum, and extract the redshift from emission or absorption lines. For Alcyoneus, photometric redshift was used, estimating distance from the galaxy's colors in multiple optical filters. This is less precise but sufficient for calculating the approximate size. With the redshift, the angular size on the sky can be converted to physical size using cosmological formulas that account for the expansion of the universe. At z approximately 0.25, the redshift of Alcyoneus, 1 arcsecond on the sky corresponds to about 4 kiloparsecs, 13,000 light-years, of physical distance. Alcyoneus's lobes span about 8 arc-minutes, 480 arcseconds, from end to end. At its distance, that translates to about 16 million light-years. The uncertainty in this measurement comes from several sources. The photometric redshift uncertainty, about 10%. The cosmological parameters, about 2%. And the measurement of the angular extent, about 5%. Every measurement in astronomy comes with error bars. The sophistication lies not just in making measurements, but in understanding and quantifying the uncertainties. Section 15. The evolution of radio galaxies over cosmic time. To truly understand Alcyoneus, we need to place it in the context of how radio galaxies evolve over the history of the universe. Because Alcyoneus didn't spring into existence fully formed. It has a history, and that history is written in its structure. Radio galaxies were more common in the early universe than they are today. When we look at distant galaxies, which means looking back in time because light takes time to reach us, we see a higher fraction of active galactic nuclei and radio galaxies compared to the nearby universe. This tells us something important. A GN activity was more prevalent when the universe was younger. There was more gas available to fuel black holes, galaxy mergers were more frequent, funneling gas toward galactic centers. The conditions were more favorable for the kind of sustained, powerful accretion that creates radio galaxies. Alcyoneus, observed at a look-back time of about 3 billion years, when the universe was 11 billion years old, exists in an era when giant radio galaxies were more common than they are today. But even in that era, Alcyoneus is extreme. The evolution of a radio galaxy follows a typical life cycle. It begins when gas becomes available to the central black hole, perhaps through a galaxy merger or through cold gas streams flowing along cosmic filaments, or through the cooling of hot gas in the galaxy's halo. The black hole begins accreting. As accretion increases, jets form. Initially, the jets are weak and may not penetrate far beyond the galaxy. But if accretion continues, the jets strengthen. They begin to plow through the interstellar medium of the galaxy itself, sweeping aside gas and creating cavities. As the jets emerge from the galaxy, they encounter the lower density intergalactic medium. Here they can propagate more easily. They extend outward, creating hotspots where they shock the ambient gas. Behind the hotspots, the lobes inflate, filled with the energetic plasma delivered by the jets. This is the growth phase. The radio galaxy expands, the lobes grow larger, and the structure becomes more prominent in radio observations. This phase can last hundreds of millions of years if the fuel supply to the black hole remains steady. Eventually, something disrupts the process. Perhaps the gas supply runs out. Perhaps feedback from the jets themselves heats the surrounding gas enough to shut off accretion. Perhaps a change in the galaxy's structure redirects gas flows away from the black hole. When accretion stops, the jets shut off. The lobes stop being replenished with fresh energy. They begin to fade. The energetic particles radiate away their energy. The lobes expand adiabatically, cooling and dimming. Within a few 100 million years, they become undetectable at radio wavelengths. This is the death phase. The radio galaxy transitions back to a normal elliptical galaxy. The lobes dissipate into the intergalactic medium, leaving only subtle imprints in the thermal and chemical properties of the gas. But sometimes, accretion restarts. Fresh gas becomes available, perhaps from another merger, or from gas cooling in the halo. The black hole turns back on. New jets form, creating new, smaller lobes superimposed on the faded remnants of the old ones. These are called double-double radio galaxies, and they show 2 generations of lobes. The old, extended, faint lobes from a previous episode of activity, and the new, compact, bright lobes from current activity. Alcyoneus doesn't show clear evidence of this double-double morphology. It appears to be in the middle of a single, sustained episode of activity. The lobes are consistent with continuous growth over several 100 million years without major interruptions. This sustained activity is unusual and part of what makes Alcyoneus special. Most radio galaxies show evidence of episodic behavior, activity turning on and off over time. Alcyoneus has apparently maintained steady jet activity for an exceptionally long period. What does the future hold for Alcyoneus? Several possibilities exist. If the jets continue at their current power, the lobes will keep growing. They might reach 20 million light years, 25 million, possibly larger. But there are physical limits. As the lobes grow larger, they become less dense and their surface brightness decreases. Eventually, they become so faint that they're undetectable even with sensitive instruments. There's probably a practical size limit around 30 to 50 million light-years, beyond which radio lobes simply can't be observed with any realistic telescope. Alternatively, the jets might shut off. This is statistically likely. No jet activity lasts forever. When the jets stop, the lobes will begin their long fade into invisibility. 100 million years after the jets shut off, Alcyoneus's spectacular radio structure will be gone, leaving only subtle traces in the hot gas distribution around the galaxy. Or the galaxy might undergo a merger. Collisions with other large galaxies could disrupt the existing lobes while simultaneously triggering a new burst of accretion and jet activity. The old lobes would be torn apart by tidal forces and Raum pressure, while new lobes form on different axes determined by the post-merger configuration. We can't predict which scenario will actually occur, but we can say with confidence that Alcyoneus as we see it now is a temporary state. The lobes will not persist indefinitely. They're maintained only by continuous energy input from the jets, and that input will eventually cease. In a billion years, Alcyoneus will look very different. The spectacular radio structure might be gone entirely, or it might have grown even larger, setting new records. Or it might have been transformed by mergers and interactions into something altogether different. This transience is important to keep in mind. When we observe Alcyoneus, we're seeing it at one moment in a much longer evolutionary story. We're lucky to catch it during its most spectacular phase, when the jets are active and the lobes are bright and extended. Thousands or millions of galaxies throughout cosmic history have probably gone through similar phases. But we see only the ones that happen to be in their active, visible phase during the relatively brief moment of cosmic time that we're observing. Alcyoneus is not necessarily unique. It's just the largest example we've found of a phase that many radio galaxies pass through. And that realization is itself profound. It means the universe has been producing structures like this throughout its history, most of which have come and gone without any observer to see them. Section 10. The Age Problem. There's another puzzle embedded in Alcyoneus's existence. It's what astronomers call the Age Problem, and it goes like this. How did this galaxy have enough time to get so big? We observe Alcyoneus as it was 3 billion years ago, when the universe was about 11 billion years old. That sounds like plenty of time. But creating radio lobes 16 million light-years across requires specific conditions sustained over hundreds of millions of years. Let's do the math. The jets propagate through intergalactic space at speeds on the order of 0.1 to 0.5 times the speed of light. Let's be generous and say they average 0.3 c, about 90,000 kilometers per second. At that speed, it would take roughly 50 million years for the jets to traverse 8 million light-years, half the total extent of the lobes. But that assumes constant speed and no interruptions, which is unrealistic. In practice, the jets slow down as they plow through intergalactic gas. They lose energy to radiation. The hot spots advance more slowly than the initial jet speed. A more realistic estimate for the age of Alcyoneus's lobes is 200 to 300 million years minimum, possibly longer. Now, that's still well within the 11 billion year age of the universe when we observe Alcyoneus? No problem, right? Here's the issue. the galaxy itself had to form first. The supermassive black hole had to grow to 400 million solar masses. The galaxy had to acquire enough gas to feed sustained accretion. All of this takes time. Supermassive black holes grow through two main channels: accretion and mergers. Accretion is limited by the Eddington rate. Even at maximum accretion, it takes about 100 to 200 million years to grow a black hole from stellar mass, tens of solar masses, to supermassive, hundreds of millions of solar masses. Galaxy mergers can speed this up by bringing together black holes that have already grown substantially. But mergers also disturb the system, potentially interrupting jet activity. The timeline gets tight. You need time for the galaxy to form, time for the black hole to grow, time for the system to settle into a configuration that allows sustained jet activity, and then time for the jets to create the enormous lobes. Add all that up, and you're using a significant fraction of the available cosmic time. Alcyoneus likely started forming when the universe was only a few billion years old. It had to evolve rapidly, assembling mass and establishing the conditions for powerful jets relatively quickly compared to typical galaxy evolution timescales. This suggests that Alcyoneus formed in an unusual environment or through an unusual pathway. Perhaps it underwent an early major merger that both grew its black hole rapidly and triggered the intense accretion that powers the jets. Or perhaps the early universe had conditions that favored the formation of such extreme objects: denser gas, more efficient accretion, different feedback processes that are less common in the later universe. We see other examples of surprisingly massive black holes at high redshift. Black holes with billions of solar masses when the universe was less than 1 billion years old. These challenge our models of black hole growth in similar ways. Alcyoneus is part of this pattern. It's not just big. It's big surprisingly early in cosmic history, and that tells us something about the diversity of evolutionary pathways galaxies and black holes can follow. Section 11. The impact on cosmic structure. Alcyoneus doesn't exist in isolation. Its jets and lobes interact with the cosmic web, the large-scale structure of matter in the universe. And those interactions have consequences that extend far beyond the galaxy itself. The cosmic web consists of filaments of galaxies connected by streams of gas, surrounding vast voids. Galaxies form at the nodes and along the filaments of this web, where matter is densest. Alcyoneus's lobes extend far beyond its host galaxy into the intergalactic medium. They're pumping energy into this medium, heating it, stirring it, affecting the distribution of gas across millions of light years. This energy injection has several effects. First, it heats the gas. The intergalactic medium around Alcyoneus is significantly hotter than it would be without the radio lobes. This heating can be measured through X-ray observations of the hot gas. Hot gas is less dense than cold gas at the same pressure, so the heated region around Alcyoneus is somewhat evacuated. There's less gas per unit volume than in comparable regions elsewhere. Second, it creates turbulence. The jets don't just heat the gas, they stir it. The lobes rise buoyantly through the intergalactic medium, dragging gas with them, creating flows and eddies. This turbulence mixes material on large scales, affecting the chemical composition and thermodynamic state of the gas. Third, it suppresses star formation in nearby galaxies. Star formation requires cold, dense gas. The heating and stirring caused by Alcyoneus's jets makes it harder for gas in nearby systems to cool and collapse. Galaxies within a few million light-years of Alcyoneus are likely forming stars at lower rates than they otherwise would. This is AGN feedback at cosmological scales. We know that AGN feedback is important within galaxies. It regulates black hole growth and star formation in the host galaxy. But Alcyoneus shows that the effects can extend far beyond the host, influencing the evolution of an entire region of the cosmic web. There's another consequence that's more speculative but intriguing. The energy deposited by Alcyoneus's lobes might affect the distribution of dark matter. Dark matter doesn't interact electromagnetically, so it's not directly heated by the radio lobes. But dark matter does feel gravity. The hot gas created by the lobes expands, creating a pressure gradient that affects the gravitational potential of the region. Over hundreds of millions of years, this could subtly reshape the dark matter distribution, creating a slightly less concentrated halo or affecting the orbits of dark matter subhalos in the region. This effect would be small. Dark matter is the dominant component by mass, so baryonic processes have limited influence on it. But in extreme cases, like Alcyoneus, even small effects might be detectable in gravitational lensing observations or in the dynamics of galaxies in the region. The point is, Alcyoneus is not just a galaxy with big lobes. It's a cosmic engine that has reshaped its environment, affecting the temperature, density, chemical composition, and possibly even the dark matter distribution across a region tens of millions of light-years across. It's a reminder that galaxies are not isolated objects. They're nodes in a connected system, and the most extreme galaxies can influence that system on scales far larger than themselves. Section 12. What happens next to Alcyoneus? Alcyoneus is a snapshot. We see it as it was 3 billion years ago. But galaxies evolve. What does the future hold for this enormous structure? There are several possible evolutionary paths. First possibility, the jets shut off. This is actually the most likely scenario over long timescales. No jet activity lasts forever. Eventually, either the black hole runs out of fuel or some change in the accretion geometry causes the jets to cease. When the jets shut off, the lobes stop being replenished with fresh energy. They begin to fade. The energetic particles radiate away their energy. The magnetic fields decay. Over tens to hundreds of millions of years, the lobes gradually disappear from radio observations. The galaxy would still be there, of course. The black hole would still be there, but the spectacular radio emission would fade, and Alcyoneus would become just another elliptical galaxy, indistinguishable from countless others except for the subtle imprints its past activity left on the surrounding gas. Second possibility, the jets restart after a period of dormancy. This happens in many radio galaxies. The black hole turns off, then turns back on later when fresh gas becomes available. If this happens, Alcyoneus might develop new, smaller lobes superimposed on the old, faded ones. We actually see examples of this in other galaxies. Double radio galaxies with 2 generations of lobes, the old ones large and faint, the new ones small and bright. Alcyoneus could follow this pattern. Third possibility, the galaxy undergoes a merger. If Alcyoneus collides with another large galaxy, several things would happen. The merger would funnel gas toward the central black hole, potentially triggering a new burst of jet activity. The black hole would merge with the other galaxy's black hole, growing even more massive. But the merger would also disrupt the existing radio lobes. The gravitational perturbations and ram pressure from the merger would tear apart the delicate structures, scattering the energetic particles and destroying the coherent lobe morphology. So a merger would end Alcyoneus as we see it now, even while potentially creating something new and different. Fourth possibility, the jets continue. If Alcyoneus maintains its current level of activity, the lobes will keep growing. They might reach 20 million light years, 25 million, larger still. But there's a limit. Eventually, the density of the intergalactic medium becomes so low that the jets can't effectively couple their energy to it. The hot spots become diffuse. The lobes become so extended that they're undetectable even with sensitive instruments. There's probably a practical size limit for radio galaxies somewhere between 20 and 50 million light years, beyond which the structures become too faint and diffuse to observe, or perhaps even to maintain coherence. Which of these scenarios will actually occur? We can't know for certain. But given what we understand about galaxy evolution and AGN life cycles, the most likely outcome is the first. The Eozil jets eventually shut off, the lobes fade, and Alcyoneus becomes a quiet elliptical galaxy, its brief spectacular phase preserved only in the thermal and chemical signatures it left in the intergalactic medium. Section 13, the search for even larger galaxies. Here's the question that every astronomer who studies Alcyoneus eventually asks: is it really the biggest? Or is it just the biggest we've found so far? The honest answer is, we don't know. And there are good reasons to think larger galaxies might exist undiscovered. The main reason is observational bias. Radio surveys have limited sensitivity. They can only detect objects above a certain brightness threshold. An object with lower surface brightness, radio emissions spread over a larger area, might fall below that threshold even if its total radio power is substantial. Alcyoneus is detectable because its lobes, while enormous, still have sufficient surface brightness to be seen by LOFAR and other radio telescopes. But imagine a galaxy with lobes extending 25 million light years. If the total radio power were similar to Alcyoneus, that emission would be spread over a larger area, reducing the surface brightness. Such a galaxy might exist, but be too faint to detect with current surveys. There's also the issue of survey coverage. No single radio survey covers the entire sky at high resolution and sensitivity. Different surveys cover different areas at different frequencies with different sensitivities. Alcyoneus was found in the LOFAR survey area, but large portions of the sky haven't been surveyed at LOFAR's frequency and resolution. There could be equally large or larger radio galaxies in those uncovered regions. The southern hemisphere is particularly undersurveyed at low radio frequencies. Most major low-frequency arrays are in the northern hemisphere. The southern sky has been observed less comprehensively. If there's a giant radio galaxy in the southern sky, we might simply not have the data to find it yet. This is changing. The Square Kilometer Array, SKA, currently under construction, will be the most sensitive radio telescope ever built, with components in both South Africa and Australia. It will survey the entire sky at multiple frequencies with unprecedented sensitivity. When SKA comes online, we'll be able to detect radio galaxies with much lower surface brightness. We'll cover regions of sky that current surveys haven't reached, and we'll almost certainly find more giant radio galaxies. Some of them might be larger than Alcyoneus. There's another possibility. Maybe there are not just larger individual radio galaxies, but a different class of object altogether. Structures even more extreme than giant radio galaxies that we haven't yet recognized or categorized. For instance, what if multiple radio galaxies are linked by their lobes? What if the lobes from two neighboring active galaxies merge and interact, creating a structure that's not just one galaxy, but two or three, working in concert? We haven't seen clear examples of this yet, but in principle it could happen. And if it does, the resulting structure could be enormous, tens of millions of light years across, maybe larger. The universe is full of surprises. Every time we build better instruments and look more carefully, we find things we didn't expect. Alcyoneus is almost certainly not the last word on cosmic extremes. It's the current record holder, but records are made to be broken. Section 14. Implications for cosmology. The existence of Alcyoneus has implications that go beyond the study of individual galaxies. It touches on fundamental questions in cosmology about how structure forms in the universe and what limits exist on that structure. One of the key parameters in cosmological models is the matter-power spectrum, essentially a description of how matter is distributed on different scales in the universe. This distribution is set by the initial conditions from the Big Bang and shaped by gravitational growth over billions of years. The power spectrum predicts how clustered matter should be on scales from individual galaxies up to the largest structures in the universe. And there's a characteristic scale, about 200 to 300 million light years, beyond which structure formation becomes inefficient. This is because the expansion of the universe counteracts gravity on the largest scales. Gravity tries to pull matter together, but expansion pushes it apart. On scales larger than a few 100 million light years, expansion wins, and structures don't grow. This sets a maximum size for gravitationally bound structures in the universe. Galaxy superclusters can be a few 100 million light years across, but they're not strongly bound. They're gradually being pulled apart by cosmic expansion. Now, Alcyoneus's radio lobes extend 16 million light years. That's well below the cosmological scale, so there's no direct conflict with structure formation limits. But here's the interesting part. Alcyoneus's lobes are not gravitationally bound. They're sustained by energy injection from the jets, not by gravity. They're a different kind of structure, one maintained by active processes rather than passive gravitational binding. This means the size limits that apply to gravitationally bound structures don't necessarily apply to AGN-powered structures. In principle, jets could create lobes much larger than 16 million light years if they were powerful enough and sustained long enough. There might not be a hard limit, just a practical one set by the finite lifetime of jet activity and the decreasing density of the intergalactic medium at large distances. This is cosmologically interesting because it means the universe can contain structures on scales that traditional structure formation models don't address. Alcyoneus is a reminder that not everything in the universe follows the standard hierarchical growth paradigm. Some structures are built from the inside out by active processes rather than from the outside in by gravitational collapse. This has implications for how we think about energy and matter distribution in the universe. A significant fraction of the intergalactic medium's energy content might come from AGN feedback, rather than from gravitational collapse and shock heating. Alcyoneus and other giant radio galaxies are major contributors to this energy budget. It also affects our understanding of galaxy evolution in context. Galaxies don't just respond to their environment, they shape it. And in extreme cases like Alcyoneus, they shape it on scales comparable to cosmological structures. Section 15. The technical challenges of the discovery. Let me pull back the curtain on the technical side of this discovery, because the process of finding and confirming an object like Alcyoneus is fascinating and reveals a lot about modern observational astronomy. The first challenge is data volume. LOFAR generates enormous amounts of data, petabytes per year. A single observation can produce terabytes of raw data. This data needs to be processed, calibrated, and imaged before astronomers can even begin to analyze it. The processing pipeline for LOFAR data is complex. It involves removing radio frequency interference from terrestrial sources, cell phones, radar, broadcast stations, calibrating the relative phases and amplitudes of the thousands of individual antennas, correcting for ionospheric effects. The Earth's ionosphere bends and distorts radio waves. Combining the signals from all antennas to create images. This processing is computationally intensive. It requires supercomputers and sophisticated algorithms. And despite the automation, human oversight is needed to catch errors and artifacts. Once the data is processed and images are created, the next challenge is source detection. Automated algorithms scan the images looking for radio sources, regions brighter than the background noise. But detecting an object like Alcyoneus is tricky. The lobes are extended and have relatively low surface brightness. Simple detection algorithms that look for compact bright sources might miss them or fragment them into multiple separate detections. The team that discovered Alcyoneus developed specialized algorithms to identify and measure extended sources. These algorithms look for patterns of emission that span large angular scales and have the characteristic morphology of radio lobes. Even with these algorithms, confirmation is needed. Could the apparent large-scale structure be a chance alignment of unrelated sources? Could it be an artifact of the imaging process? The team performed multiple checks. They examined the data at different frequencies to see if the structure was consistent. They looked at archival data from other telescopes to see if the source appeared in those observations. They modeled what a real radio galaxy of that size should look like and compared it to the observations. All the tests supported the interpretation that Alcyoneus is a single coherent structure, not a chance alignment or artifact. Then there's the distance determination. To calculate the physical size, you need to know how far away the galaxy is. For relatively nearby galaxies, you can measure spectroscopic redshift directly, observing emission or absorption lines in the galaxy's spectrum and measuring how much they're shifted by the expansion of the universe. But Alcyoneus is faint in optical wavelengths. Getting a good spectrum requires significant telescope time on a large optical telescope. The team used photometric redshift, estimating distance based on the colors of the galaxy in multiple optical filters. This is less precise than spectroscopic redshift, but sufficient for their purposes. With the distance estimate, they could convert the angular size on the sky, measured in arc minutes, to a physical size, measured in light years. The result? 16.3 million light years, with uncertainties of perhaps 10 to 20%, depending on the exact redshift and cosmological parameters used. This technical work, data processing, source detection, confirmation, distance measurement, is invisible to most people but absolutely essential. Without it, discoveries like Alcyoneus wouldn't happen. Section 16. The future of radio astronomy. The discovery of Alcyoneus is, in many ways, a preview of what's coming in radio astronomy. We're entering a golden age of radio observations, with new instruments that will revolutionize our understanding of the universe. The square-kilometer array is the most ambitious. When complete, it will have a collecting area of 1 square kilometer, hence the name, distributed across thousands of antennas in South Africa and Australia. SKA will be about 50 times more sensitive than current radio telescopes. It will be able to detect radio sources that are currently invisible. It will map the entire sky repeatedly at multiple frequencies. For giant radio galaxies, this means several things. First, we'll find more of them. Objects that are currently too faint to detect will become visible. The census of giant radio galaxies will expand from hundreds to potentially thousands. Second, we'll be able to study known ones in greater detail. We'll resolve fine structure in the lobes. We'll trace the magnetic field configurations through polarization observations. We'll detect fainter parts of the radio emission that current telescopes can't see. Third, we'll be able to do statistical studies. With large samples of giant radio galaxies, we can ask questions like, what fraction of all radio galaxies become giants? Is there a correlation between galaxy size and environment? How does the occurrence rate of giant radio galaxies evolve with cosmic time? Another transformative instrument is the Next Generation Very Large Array, NGVLA, planned for construction in the southwestern United States. This will be a replacement and upgrade to the current VLA with much higher sensitivity and resolution. NGVLA will excel at high-frequency observations, complementing SKA's focus on lower frequencies. Together, these instruments will give us a complete picture of radio galaxy spectra from tens of megahertz to tens of gigahertz. There's also LOFAR 2.0, an upgrade to the existing LOFAR array. This will increase sensitivity and expand the frequency coverage, making it even better at detecting the kinds of extended, low-surface brightness structures that characterize giant radio galaxies. And in space, there are proposals for radio telescopes on the far side of the Moon. The lunar far side is the only place in the solar system that's permanently shielded from Earth's radio interference. Telescopes placed there would have unprecedented sensitivity to low-frequency radio waves. Such instruments could detect radio emission from the earliest phases of galaxy formation, perhaps even from the very first black holes forming in the first galaxies. They might find giant radio galaxies at such high redshifts that we're seeing them when the universe was less than 1 billion years old. The point is, Alcyoneus is not the end of the story. It's the beginning. The tools we're building will reveal a radio universe far richer and more complex than what we know today. And those revelations will force us to update our models, refine our theories, and expand our understanding of how the universe works. Conclusion. So here's where we are. We've discovered Alcyoneus, a galaxy with radio lobes extending 16.3 million light-years from end to end, the largest known galaxy in the universe. It's powered by a supermassive black hole 400 million times the mass of the Sun, which has been feeding continuously and launching powerful jets for hundreds of millions of years. It's reshaped the intergalactic medium across an enormous volume, heating gas, suppressing star formation in neighboring galaxies, and leaving an imprint that will persist for billions of years. It challenges our models of how galaxies form and evolve. It forces us to ask new questions about black hole growth, jet physics, and the limits of structure formation in the universe. And it's probably not alone. There are likely other giant radio galaxies out there, waiting to be found by the next generation of radio telescopes. Some of them might be even larger. Alcyoneus is a reminder that the universe still holds surprises, that our models and theories, good as they are still incomplete, that there's more out there than we've yet discovered. It's also a reminder of the incredible power of black holes. A single object, not much larger than our solar system, can affect the universe across distances of millions of light-years, can pump out energy equivalent to trillions of stars, can reshape the cosmic web itself. And it's a reminder of human ingenuity. We built telescopes sensitive enough to detect these faint structures. We developed algorithms smart enough to find them in petabytes of data. We created models sophisticated enough to interpret what we're seeing. Alcyoneus is out there, 3 billion light-years away, ejecting jets into the cosmic void, utterly indifferent to our existence. It was doing this long before humans evolved. It will continue long after we're gone. But for this brief moment in cosmic history, we're here to see it, to measure it, to try to understand it. And that's remarkable. The discovery of Alcyoneus opens new chapters in multiple areas of astrophysics. It tells us about black hole accretion in extreme regimes, about jet physics at unprecedented scales, about feedback processes that shape galaxies and the intergalactic medium, about the history and evolution of the universe itself. Each measurement we make of Alcyoneus, its spectrum, its polarization, its morphology, its environment, adds to our understanding. Each simulation we run to reproduce its properties refines our models. Each comparison we make with other giant radio galaxies improves our grasp of the underlying physics. This is how science works, not through single revelations, but through the gradual accumulation of observations and insights, each building on the last, each expanding the boundaries of what we know. Alcyoneus is one galaxy, but it represents something larger. It represents the frontier of our knowledge, the edge where observation meets theory, where data challenges our assumptions. It reminds us why we explore, why we build telescopes and launch satellites and spend careers analyzing data. Because there's always something more to discover. Always something that surprises us. Always something that teaches us that the universe is more complex, more diverse, more extreme than we imagined. The radio lobes of Alcyoneus stretch across 16 million light-years of space. Light from one end of the structure takes 16 million years to reach the other end. When that light left one lobe, our hominid ancestors hadn't even split from other apes yet. By the time it reaches the other lobe, who knows what life on Earth will have become? We exist in a universe where such structures can form, where black holes can pump energy across distances that dwarf galaxies, where jets can maintain their coherence and power across timescales longer than the entire evolutionary history of complex life on Earth. That's awe-inspiring and humbling and motivating. Because if the universe can create something like Alcyoneus, if physics allows structures this extreme, this powerful, this vast, what else is out there waiting to be discovered? The Square Kilometer Array will be fully operational within a decade. It will survey the sky with sensitivity and resolution that makes current telescopes look primitive. It will find more giant radio galaxies, larger ones, probably, objects we can't yet imagine. The next generation. Very Large Array will complement SKA with high-frequency observations. The James Webb Space Telescope will study the host galaxies of radio galaxies in optical and infrared wavelengths, revealing their stellar populations and star formation histories. Future gravitational wave detectors might even catch the merger events that create supermassive black holes like the one powering Alcyoneus, giving us direct observations of black hole growth in real time. The story of Alcyoneus isn't ending, it's just beginning. This discovery is the opening chapter of a much longer narrative about giant radio galaxies, about black hole physics at extreme scales, about the evolution of structure in the universe. And we get to be here for it. We get to witness the discoveries, understand the physics, appreciate the scope and scale and sheer audacity of what the universe produces. If you made it this far, thank you for exploring this with me. Alcyoneus is one of those discoveries that changes how you think about scale, about time, about the capacity of nature to produce phenomena far beyond anything we experience in daily life. Drop a comment and let me know. Does knowing about Alcyoneus change how you think about the scale of the universe? What do you think we'll find when the next generation of radio telescopes comes online? And does it make you wonder what else is out there just beyond the limits of our current instruments? I'll see you in the next video, where we'll probably find something even bigger, even more extreme, even more unexpected. Because in this universe, there's always something waiting to surprise us. The cosmos has more stories to tell, and we're learning to listen. Stay curious, stay amazed, and keep looking up, or in this case, keep tuning in to those radio frequencies, because that's where the biggest structures reveal themselves. The universe is vast. The universe is strange. The universe contains objects like Alcyoneus, galaxies so large they shouldn't exist according to our models, yet there they are, pumping energy across millions of light years, reshaping the cosmos on scales we are only beginning to comprehend. And the best part? We're just getting started.